So we will continue our discussion of compactness. Towards the end of the last class, I said that in the real line, a set is compact if and only if it is closed and bounded. Okay. And we shall prove that today. But instead of proving that directly, we shall prove a theorem which is more general than that, and that will come out as a consequence of it. Okay. We shall give several statements which are equivalent to the compactness, and use of that is that we can use any one of those statements to prove or check whether a given set is compact or not. So that theorem is as follows. These are, you can say, various characterizations of compactness. Okay, so let us say that let X_T be a metric space. Okay. Then what we want to say is that the following statements are equivalent. Okay. That is this is the standard short form used for that, TFAE. That means the following are equivalent. Following statements are equivalent. Okay. And what it means is that if one of the statements is true, all the statements are true. If one of them is false, all are false. Okay. So first of that is X is compact. Okay. So that is why we call this characterizations of compactness. Okay. Second is that if you take any infinite set in X, okay, then that has a limit point. Okay. So every infinite subset of X has a limit point. Every infinite subset of X has a limit point. Okay. This is sometimes called Bolzano-Weierstrass property. Okay. If a metric space has this property that every infinite subset has a limit point, that metric space is said to have a Bolzano-Weierstrass property. Okay. So what we are saying here is that compactness is equivalent to Bolzano-Weierstrass property in case of metric space. Then third is every sequence in X has a convergent subsequence. Every sequence in X has a convergent subsequence. This Bolzano-Weierstrass property is a, for example, is a term used in Siemens. Okay. Similarly, this property is described by saying that X is sequentially compact. Okay. If a metric space has this property that every sequence has a convergent subsequence, we say that X is sequentially compact. Okay. So there is another way of saying the same thing is that X is sequentially compact. So what this theorem says is that in case of metric spaces, compactness and sequential compactness, these two things are the same. This is not true in arbitrary topological spaces. Okay, in arbitrary topological space, compactness and sequential compactness are different, but let us not go into that. Okay. And lastly, X is complete and totally bounded. Totally bounded. Okay. All right. Now, when we want to prove the equivalence of all these statements, one can proceed in the various ways. For example, one can show that 1 is 1 if and only if 2, 2 if and only if 3, etc. Or one can prove 1 implies 2, 2 implies 3, 3 implies 4, and then 4 implies 1, or any cycle like that. Okay. We can choose any cycle like that and go over to proof. But even before going to the proof of this, let me say how the Honey-Borel theorem follows from this. Okay. So let me write that as a corollary. okay, let us say corollary 1, okay, that is any Borel theorem. Okay, so what does theorem say? That if a subset of a real line with the usual metric is compact if and only if it is closed and bounded. Okay, so a subset of R is compact if and only if it is closed and bounded. Okay. Okay. Now, how does this follow from this theorem? Okay. Of course, we have already seen one thing, that if a set is compact, then it is closed and bounded. That is true in any metric space. Only issue is to prove the converse. Okay. Okay. But we already know that R is a complete metric space. Okay. And we have shown that a closed subset of a complete metric space is complete. Right. So if you take a subset which is closed, then that is complete. Okay. And we have also shown that in R every bounded set is totally bounded. Right. In R every bounded set is totally bounded. So if a set is closed and bounded, then it is complete and totally bounded. So that is this last sentence. If X is complete and totally bounded, 4 implies 1 will say that X is compact, right. So if we prove this theorem, that will follow. Okay, that will follow. Okay. All right. Let me also recall one more well known theorem that we have proved in the case of sequences. Okay. We have shown that in fact that was called Bolzano-Weierstrass theorem at that time. Okay, let me just write, that was called Bolzano, that is namely that every bounded sequence has a convergent subsequence. Okay, every bounded sequence of real numbers has a convergent subsequence. Of course, we have proved this earlier using the ideas of limit superior, limit inferior, etc. But you can see that this also follows immediately from this, okay? Because what we can say is that if a sequence is a convergent sequence, okay, suppose xn is a bounded sequence, then we can always find an interval, let us say interval AB, such that each xn lies in that interval. Okay, if xn is bounded, we can say that xn belongs to some interval AB for all n. Okay, okay, all right. Now this set is closed and bounded, and hence compact. Okay, and once a set is compact, we are saying that every sequence in AB must have a convergent subsequence. Okay, so this also follows from this theorem. Okay, so this is a very powerful theorem. It gives various characterizations of compactness. Okay, and it has lots of uses also. So let us go to the proof of the theorem. Okay, as I said, we can start proving in one cycle. Let us attempt this way: 1 implies 2, 2 implies 3, etc. If we get into some problem, let us see. Okay, so let us start with 1 implies 2. Okay, 1 implies 2 means what? We assume that X is compact and show that every infinite subset has a limit point. Okay, so let X be compact. And suppose that infinite subset is A. Let us say A be an infinite subset. Infinite subset of X. Okay. Now, if this subset of this subset A, suppose 2 is false, then it means that this subset does not have any limit point. Okay, all right. Now if it does not have any limit point, what does it mean? Suppose if you take any x in x, okay, then that x is not a limit point, okay, that x is not a limit point. So suppose A has no limit point in x, suppose A has no limit point in x, that means what, if you take any point x in x, any point small x in big X, that x is not a limit point of A, okay. Now what does that mean? If you look at a definition of limit point, we say that if you take any open ball with center at x, that should contain at least one point from A other than x itself, okay, other than x itself, okay. So if something is not a limit point, it means that there exists an open ball, okay, which does not contain any point of A other than x itself, if at all x belongs to A. If x does not belong to A, then no point from A. If x belongs to A, then just singleton x, okay, intersection with that ball with A will be just singleton x, okay. So this means that, that means for every x belonging to x, okay, there will exist a ball with radius r, that r may depend on x, okay. So I shall denote that by r suffix x, okay, for x in x there exists r suffix x bigger than 0, such that suppose you take an open ball with center at x and radius this r suffix x, okay, this does not contain any point other than any point of A other than x itself in case x belongs to A, okay. So you can say that let us write it, that this intersection A, we will say that this is empty if x does not belong to A, okay, this is empty if x does not belong to A, and this is equal to singleton x if x belongs to A, okay. Now if you take a collection of these open balls, see this u x r x obviously contains x, okay. So suppose you take the collection of all these open balls for every x in x, then that is a open cover of x, okay, that is an open cover of x, that is you take all such open balls u x r suffix x for x in x, okay, this is an open cover of x, this is an open cover of x, okay. It's an open cover of x, okay, and since we have assumed that x is compact, okay, so this must have a finite subcover, okay, this must have a finite subcover, okay. So is an open cover of x, and since x is compact, this is the usual argument, since x is compact it has a finite subcover. Okay, I will remove this part. Okay. Now what does this mean? This finite subcover of this means what, there should exist some n points, let us say x1 x2 xn, such that x is contained in union of those n balls, okay. So that is, I will say that is there exists x1 x2 xn in x such that x is contained in union, let us say xj, and then r suffix xj, j going from 1 to n, okay, alright, and A is obviously a subset of x, so A is also contained in this, okay. So A is contained in union of a finite number of balls like this, okay, but each of these balls can contain just one point of A at the most, okay, and we started with saying that A is an infinite set, okay, so that is a contradiction, right, okay, there are only finite number of balls and we say that A is contained in their union, but each of those ball can contain at most one point of A, okay. So that will say that A must be finite, okay, right, and that is a contradiction, okay. Okay. So that proves that 1 implies 2, is it okay? Let us now attempt 2 implies 3, okay. That means what? We should assume that every infinite set has a limit point, and from that we will try to prove that every sequence in X has a convergent subsequence, okay. Okay. So our assumption now is 2, that is every infinite subset of X has a limit point, okay. Alright, let us say that let Xn be a sequence, let Xn be a sequence in X, okay. We have to show that this sequence has a convergent subsequence, okay. And if we want to use 2, namely that every infinite set has a limit point, we have to start, if we want to use that, we have to start with some set, not a sequence, okay. But does not matter, every sequence also will lead to a set, that is namely the range of that sequence, okay. That is, you consider a set of all these points Xn, okay, that is suppose let's suppose I call that set A, let A be equal to Xn, n belonging to n. In other words, what we would have described usually, because if we know that every sequence is a function, okay, so this is the thing, but what you can call range of that function, okay. You take the set of all those points which form the sequence, okay. There are of course 2 possibilities, okay, that A may be finite or A may be infinite, okay. If A is finite, okay, is it clear that at least one member of A must repeat infinitely many times in the sequence? If the range of a sequence is finite, at least one, of course more than one also may repeat, but at least one will repeat infinitely many times, okay. You take that particular subsequence, that is obviously convergent subsequence, okay. So let us say that if A is finite, okay, at least one member of A repeats infinitely, at least one member of A repeats infinitely many times, okay. In other words, we can extract a constant subsequence out of Xn, okay. You just take that particular, wherever that, for example suppose x1, x3, x7 they are all same, you just take that particular subsequence, okay. So that is, we can say that is Xn has a constant subsequence, okay, right. So if A is finite, there is no problem. If A is infinite, what can we do, okay, then we use that, we have said, we assume that every infinite subset must have a limit point, okay. If A is infinite, then A must have a limit point in X, okay. In particular, limit point is a point in the closure, its a limit point means its distance from A is 0, okay, which means you can always find a sequence in A which converges to that point, okay, and we can choose that sequence in such a way that it is a subsequence of this, okay, right. So let us say that, let us complete this argument. If A is infinite, then A has a limit point suppose I call it limit point X, say X, small x belonging to capital X, okay. And then since, remember we have already shown that if you take any point in the closure, okay, then you of closure of a set, then you can find a sequence of elements of that set converging to that point. So if a limit point is in particular point in the closure, so we can always, for example, if you take any open set with x as the center, then it should contain some point in A other than x itself, okay. So suppose first you take a radius, let us say 1 by n, okay, then you will find some element here, you will find some element here such that distance between x and that element is less than 1 by n, okay. Suppose that element is, let us say, some x20, okay, then you take the let us say next number, then you can choose the next x nk, which is where nk is bigger than that 20. Basically what we need is to choose a subsequence, we need these indexes n1 n2 etc strictly increasing, but that can be done, okay, that is not a big problem. So what I will simply say is that then we can construct a subsequence of xn converging to x, okay. Then there exists a subsequence xnk of xn converging to x. Okay. So we have proved in both the cases, if A is finite or A is infinite, in both cases xn has a convergent subsequence, right, okay. So we have proved 2 implies 3, that means, or using this terminology, Bolzano-Weierstrass property implies sequential compactness, okay. Alright, now let us go to this, okay, 3 implies 4. Okay, again remember what is it that we need to prove, that assume that every sequence has a convergent subsequence, okay, and using that we need to prove 2 things. First is that x is complete, okay, and second thing is x is totally bounded, okay. Alright, let us look at this first. To show that x is complete, what do we need to prove? We need to prove that every Cauchy sequence is convergent, okay, every Cauchy sequence is convergent. So let us start with that. So let xn be a Cauchy sequence in x, be a Cauchy sequence in x. Okay, but our assumption 3 is that every sequence has a convergent subsequence, right. So in particular this Cauchy sequence also has a convergent subsequence, okay, okay. So let xn then so let us say 3 implies that xn has a convergent subsequence. Okay, and we have observed long ago, okay, that if a Cauchy sequence has a convergent subsequence, then the sequence itself is convergent, okay. Either we have proved it in the class or it is one of the problem sheets, okay. So if a Cauchy sequence has a convergent subsequence, then the sequence, original sequence itself converges, okay. So then xn itself converges, okay. Okay, so this shows that x is complete, okay, this shows that x is complete. So we have shown that every Cauchy sequence is convergent, hence x is complete. Okay, so what remains? We need to show this last thing, okay, that x is totally bounded, okay, x is totally bounded, okay. Alright, now to show that x is totally bounded, okay, let us recall the definition. What is meant by saying it is totally bounded? That given any epsilon, okay, there should x, we should be able to cover x by a finite number of balls with radius epsilon, okay. So suppose that is false, okay, suppose that is false, then what does it mean? That if you take, there should exist some epsilon, okay, such that you cannot cover x by a finite number of balls with radius epsilon, okay, right. Okay, so let us start with that. Okay. Suppose X is not totally bounded, not totally bounded. Okay. Then there exists epsilon. There exists epsilon such that whichever finite family of open balls radius epsilon you take, that will not cover X. Okay. Then there is epsilon such that X cannot be covered. Let us say X cannot be covered by a finite number of open balls with radius epsilon. Okay. Okay. All right. Now we proceed as follows. Using this, we can construct a sequence which cannot have any convergent subsequence. Okay, that is the idea. Okay, so how do we construct? We start with any arbitrary element x1. Okay, let x1 belong to x. Let x1 belong to x. Okay, then we know that this u x1 epsilon cannot cover x. Okay, u x1 epsilon cannot cover x. That means there should exist some x2. There should exist some x2 which should be outside this. Okay, right. So we can let us just write this argument. Since u x1 epsilon does not cover x, there exists x2 in x minus u x1 epsilon, right. That is, there should exist some x2 which is outside this ball. Okay. Alright. Now what I do is that I will consider u x1 epsilon and u x2 epsilon. Okay, that is, consider these two balls, u x1 epsilon and u x2 epsilon. Okay, these two balls also cannot cover x, because our assumption is that x cannot be covered by a finite number of open balls. Okay, so that means I can find some x3. I can find some x3 which is outside both of this. Okay, which is outside both of this. Okay, so again the same, by the same argument, what will be the argument here? Since u x1 epsilon and u x2 epsilon, this is a finite number of open balls that does not cover x, so there must exist x2, sorry, there must exist x3 which is outside union of these two balls. Okay, so we can say, let me just write it here. So there exists x3 in x minus union, let me say j going from 1 to 2 u xj epsilon. Okay, so we have now at this stage we have constructed the first three elements of the sequence, x1, x2, x3. Okay, right. We can construct in a similar way, but before proceeding further, just observe what is the property of these three elements x1, x2, x3. It is that the distance between any two of them is bigger than or equal to epsilon, right. Okay, because why distance between x1 and x2 is bigger than epsilon? Because x2 is outside u x1 epsilon. Okay, and why distance between x3 and either x2 or x1 is bigger than or equal to epsilon? Because x3 belongs to neither to this ball nor to that ball. Okay, right. So that is important. Okay, so we can say, proceeding in this way, we can construct a sequence. Suppose we have constructed n such balls, then union of those n balls also cannot cover x, so there will exist some xn plus 1. Okay, there will exist some xn plus 1 which is outside union of those n balls. Okay, in this way, by induction, a sequence can be constructed. Okay, so I will simply say, proceeding in this way, so proceeding in this way, we construct a sequence sequence xn such that, what is the property of the sequence, that xn plus 1 does not belong to any of those n balls with center at xj and radius epsilon for j going from 1 to n. Okay, so let me just write that last thing, such that xn plus 1 belongs to x minus union open balls with center at xj epsilon j going from 1 to n, and this happens for all n. Okay. Okay. So what it means is that if you look at instead of x1 x2 x3, now if you look at x1 x2 xn plus 1, then the distance between any two of those elements is bigger than or equal to epsilon. Okay, and since this is the, and at each stage we have used this property that x is not covered by a finite number of open balls with radius epsilon. Okay, that is the property which we have used again and again. Okay, all right. So finally, what is the property of this sequence then? It is that the distance between any two elements of that sequence will be bigger than or equal to epsilon. Okay, so I can say that then distance between xn and xm is bigger than or equal to epsilon for all n and m. Okay, for all n and m. Okay. Now, can such a sequence have a convergent subsequence? Okay. Right? Obviously not, because if you take some epsilon which is less than, for example, suppose you take epsilon by 2, okay, then there will not contain, there will exist no n0 for that which will contain all elements of that sequence. Okay, so such a sequence will not have any convergent subsequence. Okay, then thus xn has no convergent subsequence. Convergent subsequence. Okay, and that contradicts this sequential compactness. Okay, right. We were trying to prove 4 using 3. Okay, our assumption was that every sequence has a convergent subsequence. Okay, and we have shown that if x is not totally bounded, we can construct a sequence which has no convergent subsequence. Okay, so this must be false. Okay, so x must be totally bounded, right. Okay, so what is left now? So we have proved 1 implies 2, 2 implies 3, and 3 implies 4. Okay, so what is remaining is this last thing, 4 implies 1. Okay. Okay, so what is assumed now, that x is complete and totally bounded. Okay, using that we have to show that x is compact. Alright. Okay, now to show that x is compact, let us proceed in the usual way. How does one start showing that something is compact? Think of some open cover, takes any open cover of x and show that it has a finite subcover. Okay, so suppose, okay, so let us okay, let G I belonging to I be an open cover of x. Okay. Okay. Now suppose this has no finite subcover. Okay, suppose this has no finite subcover, then we will get a contradiction to these things. Okay, suppose this has no finite subcover. Okay, okay. Alright, now to get a contradiction we have to use this fact that x is complete and it is also totally bounded. I will use this part first. Since x is totally bounded, we know that if you take any epsilon, x can be covered by a finite number of open balls with radius epsilon, and this is true for any epsilon. I will start with, let us say, epsilon is equal to 1, okay, let epsilon is equal to 1, okay. Then X is covered, by a finite number of open balls with radius 1, okay. Suppose those balls are suppose I call those balls as u1, u2, un. See, that is, each of this ball is, let us say, center x1 and radius 1, then center x2 and radius, okay. For the time being I do not bother about the centers, okay. What is important is each of this ball is of radius 1, okay, and so x is contained in the union of this finite number of balls, okay. So x is contained in u1 union u2 etc., union un, okay, alright. Now the next step is crucial, okay. Suppose it so happens that each of these balls u1, u2, un, okay, has a finite subcover from this, okay, has a finite, let us give some notation for this because it is something that we are going to use again and again. Suppose I call this script G, that script G is of some family of open sets which covers X, okay, right. Suppose you can find a finite subfamily which covers u1, again some finite subfamily which covers u2, and some finite subfamily which covers un, okay. Then what will that mean? Suppose you take union of all those finite subfamilies, you will again get a finite subfamily, and that will cover X, because X is contained in union of this, right, okay. But we have started with the assumption that that is not true, okay, that this has no, that will mean that this cover has a finite subcover, okay, but we have started with the assumption that is not true, okay. So what must happen, that at least one of these sets does not have a finite subcover, okay, at least one of these set does not have a finite subcover from this, okay, that is the first crucial step, okay. Then at least one of u1, u2, un does not have, or let us say u1, u2, un is not covered by a finite subfamily of G, finite okay. I will just call that I will just assume that u1 is that set, okay, it does not matter, it can be u3 also, u7 also, whichever is the set, that set I will call as u1, okay, right. So we can assume that so let us say is not covered by, let us assume that that set is u1, okay, let u1 be that set, okay. Let us again recall what is u1. u1 is an open ball, okay, let us say that suppose u1 is nothing but u, let us say x1 1, okay, that is, it is an open ball with some center and radius 1, and what is the property, that it is not covered by a finite subfamily of this script G, okay, finite subfamily of this script G, okay. Now what I will do is that I will take a closed ball, with the same center and the same radius, okay, right. So let f1 be the closed ball with the center at x1 and radius 1, so that is okay. then F1 is also not covered, F1 is also not covered by a finite subfamily of G, because F1 contains U1, okay. So then F1 is not covered by a finite subfamily of G. Okay, all right, okay, that is one property of F1. What is the second property? I will also want you to note that diameter of F1 is 2, right, okay, diameter of F1 is 2, the radius is 1, so diameter is 2, okay. There is one more property of F1, namely that F1 is contained in X. F1 is a subset of everything is happening inside X, okay, and X is totally bounded, okay, and we observed yesterday that every subset of a totally bounded subset is again totally bounded, right, every subset of a totally bounded subset is again totally bounded. So F1 is also totally bounded, okay, F1 is contained in X, so F1 is totally bounded, okay, hence F1 is totally bounded. Totally bounded, okay, okay. So next what I will do is that instead of taking epsilon equal to 1, now I will consider epsilon is equal to half, okay, that is now I will consider open balls with radius half, okay, open balls with radius half, okay, and whatever I did for X and 1, okay, the same argument I will now do for F1 and half, okay. F1 is not totally bounded, okay, so it cannot be covered by a finite number of F1 is totally bounded, so it can be covered by a finite number of open balls with radius half, okay, finite number of open balls with radius half, okay. Now each of those open balls with radius half, if each of them had a finite subcover from G, okay, then it will mean that F1 also will have a finite subcover from G, okay, but that is false, okay, that means there exists at least one ball with radius half, okay, which has no finite subcover from G, okay, which has no finite subcover from G, okay, and that open ball must I will now consider F1 itself as a metric space, okay, I will consider F1 itself as a metric space. I will not consider open balls with which in X, but open balls inside F1, okay, open ball, that means I will take elements only from F1, okay, I will take elements only from F1. So suppose we do that, then I will get a next subset F2, that is F2 will be contained in F1, F2 will be contained in F1, and what is the property of F2? F2 does not have a finite subcover from G, okay, and diameter of F2 will be less than or equal to, diameter of F2 will be half of, because now I reduce the radius, okay, it will be half of this diameter, okay, right. So let us say, so we can say that considering epsilon is equal to half, considering epsilon is equal to half and applying the same argument, we get F2 will be a closed ball with, let us say, center at x2 and radius half, which is, of course this ball is not a ball in X, okay, but it is a ball in F1. If you want to emphasize that, you can say, okay, or you can say that it is a ball in X2 intersection F1, okay, it is a ball in, even that is also fine, okay, it does not matter, okay, this intersection F1, whichever way you do. The point is that this F2 has the property that F2 is, there are three properties, okay, first is F2 is closed, F2 is contained in F1, and F2 is not covered by a finite, F2 is not covered by a finite subfamily of G, finite subfamily of G. And diameter of F2 is 1, okay, 1 or less than or equal to 1, okay, diameter of F2 is less than or equal to 1. Okay, and F2 is also totally bounded, okay, F2 is also totally bounded, okay. So now I hope it is clear to you how to proceed, okay. Now next stage I will take the radius as 1 by 4, okay, next stage I will take radius as 1 by 4 and apply the same argument to F2, okay. So suppose I do that, what I will get, I will get a next set F3 that is contained in F2, okay, that is contained in F2, okay, and F3 is also not covered by any finite subfamily of this set of this cover G, okay. So suppose we proceed in this manner, what is going to be the ultimate result? You will get a decreasing sequence of closed sets, okay, you will get a decreasing sequence of closed sets with each of Fn has all those properties, okay, each of Fn has all those, each Fn has all those properties, okay. So let me just write this argument. So we will simply say, proceeding in this way we get a decreasing sequence of closed sets, okay. Proceeding in this way we get a decreasing sequence let us say Fn, decreasing sequence Fn of closed sets okay. Let us again say decreasing means what, that is Fn contains Fn plus 1, Fn contains Fn plus 1 for all n, then diameter of Fn plus 1 is less than or equal to diameter Fn by 2, okay, or we can say exactly how much that will be, some 2 to the 1 by 2 to the power n minus 1 or whatever, okay, that is not very important, okay. So diameter of Fn plus 1 is less than or equal to diameter of Fn by 2, okay, fine. And I believe if you continue like that you will get this whole thing less than or equal to 1 by 2 to the power n, okay, 1 by 2 to the, because diameter of F1 was 2, okay, so diameter of F2 is less than or equal to 1, etc. So in general you will get diameter of Fn plus 1 is less than or equal to 1 by 2 to the power n, okay, fine. And most important, none of these Fn's can be covered by a finite subfamily of G, okay, and Fn cannot be covered by a finite subfamily of G. Of the script G. Now we have all the ingredients required to complete the proof. Remember once again we have assumed that we have assumed 4, okay. So till now we have been using the total boundedness of X, we have not yet used the completeness. We have assumed that X is complete and totally bounded, okay, and in the, remember we have proved Cantor's theorem, okay, for a complete metric space. What did we prove? That if you take any decreasing family of closed sets, okay, such that if the diameter of Fn tends to 0, then its intersection consists of just a singleton point, okay. So we can say that by Cantor's intersection theorem, intersection of Fn consists of just single point, okay. So by Cantor's intersection theorem, remember it is important here to know that X is complete, because then only we can use Cantor's intersection theorem, okay. It is not true in incomplete spaces. So by Cantor's intersection theorem, intersection of all these Fn is just a singleton set X, okay, right, okay. Now you will guess how we will complete the proof. Okay, now this x is some element in x. Okay, right, and we have started with assuming that this is a cover of x. Okay, so x must belong to one of these sets here. Okay, x must belong to one of these sets here. Okay, so we can say that, suppose I call that set some gi. So there exists, let us say there exists I in I, small I in big I, such that x belongs to gi. Okay, but this is an open set. Okay, this is an open set. Okay, so if x belongs to gi, there should exist some r such that open ball with center at x and radius r must be inside gi. Okay, right, so then there exists r bigger than 0 such that open ball with center at x and radius r that is contained in gi. Okay, all right. Okay, now look at the relationship. Now remember that x belongs to each of this fn. Okay, x belongs to each of this fn. Okay, so if there are two possibilities, if fn is contained inside this, remember x belongs to each other, so intersection of u and fn should at least contain x. Okay, there are two possibilities, either fn may not be inside uxr or fn may be, some elements of fn may be outside uxr. Okay, but if some elements of fn are outside uxr, then diameter of fn must be at least, see, remember, let us just draw the picture. Okay, see, this is x and this is the radius r. Okay, this is the radius r. Okay, now suppose you take some set fn, okay, fn contains x, and suppose fn contains some point outside uxr also. Okay, then is it clear that diameter of fn must be bigger than or equal to r by 2? Okay, that is because here there are, okay, now bigger than or equal to r. Okay, because there is some point, distance between this point and this point is bigger than or equal to r. Okay, so if fn is not inside, okay, let us say, is this argument clear? If fn does not is not contained in uxr, if fn is not contained in uxr, then diameter of fn must be bigger than or equal to r. Okay, why? Let me again repeat, because x belongs to fn, and if fn contains some point outside this ball, then it means it contains 2 points, distance between whom is bigger than or equal to r. Okay, all right. Now can this happen for every fn? We know that diameter of fn tends to 0. Okay, we know that diameter of fn tends to 0, so we can always find some large value of n such that diameter of fn is strictly less than r. Okay, but if that is the case, then that fn must be completely contained inside this. Okay, right, so we can say that since diameter of fn tends to 0, we can always find some fn, so we can say there exists, in fact we can say more. Okay, there exists some n0 such that for all n bigger than or equal to n0, diameter of fn should be less than r, but that is not very important, it is a decreasing family. If diameter is less than r for some fn, for all n bigger than or equal to that, it will be less than that, because it is a decreasing family. So let me simply observe that there exists n in n such that diameter of fn is strictly less than r. Okay, but if that is the case, that fn must be a subset of ux. Okay, then fn is contained in uxr. Okay, and remember this uxr is contained in g1. Okay, uxr is contained in g1. Okay, can this happen? Okay, because we have observed that no Fn can be covered by a finite subfamily of script G, whereas here we have showed that for large values of n, Fn is contained in just one set, okay. Fn is just contained in just one set from here, so that is a contradiction, right, okay. So that proves that if X is complete and totally bounded, then X must be compact. Is that clear? Okay. Right. So that proves the equivalence of all these conditions, and we have already seen that this theorem implies in particular Heine-Borel theorem, namely that in a real line a set is compact if and only if it is closed and bounded. It also implies Bolzano-Weierstrass theorem, namely that every bounded sequence of real numbers has convergent subsequence. Okay. We will stop with that for today.